Hey, today I want to introduce one of the most important techniques used in signal analysis, called discrete Fourier transform, or simply DFT. Well, actually DFT is a misnomer, since technically this should be called discrete time Fourier series. But DFT is such a popular name and technique that it's used in literally millions of publications that I will leave it alone as is. So, DFT is the basis for harmonic or spectral analysis. It is also called Fourier analysis. The overall idea that is any signal could be written approximately as a sum of sinusoidal waves. Typically this is an infinite sum of sinusoidal waves. As with many other mathematical things, harmonic analysis was developed long before Fourier, and many famous people were involved in it. Initially Bernoulli and Euler developed differential equations for musical string vibration description. Now we call these formulas Fourier series. Actually, Fourier himself extended the theory for heat flow in space and proposed to use Euler formulas for different functions with discontinuities. What he proposed was mathematically incorrect, but the problem was corrected later by a different mathematician, and his name is Dirichlet. As that frequently is the case, famous administrators and mathematicians of that time, including Fourier's own mentor Lagrange, didn't believe that this proposal made any sense. So, due to strong objections, the published work was not well known outside of France and was translated into English only about 50 years after Fourier's death. The point is that you should not be discouraged if your mentor does not believe in your theories. While different mechanical Fourier transformers and inverse Fourier transformers were invented by scientists like Lord Kelvin, who is famous for the second law of thermodynamics and absolute temperature, or Michelson, who is famous for measuring the speed of light from Michelson-Morley experiment, the Fourier analysis became really popular only less than 100 years ago, with the invention of computers. The real craziness started after publication of the famous FFT paper, which is fast Fourier transform algorithm. And it was algorithm by Cooley and Tukey, and they published that in 1965. The FFT is not any kind of new Fourier transform. It is just very efficient implementation of DFT. Alright, so let's see what this is all about. Sine waves are defined by their amplitude, frequency and phase. Frequency is a reciprocal of the period interval, and the phase is shift in time from the origin. Any sinusoidal function of time t could be written as amplitude A times sine of 2 pi f, and f is frequency, times time t, and plus some phase phi. Now let's try to see a few simple Fourier series examples. A constant signal x of t equals to 2 is actually a sine wave with amplitude 2, 0 frequency, and shifted by pi half or 90 degrees to the left, which is basically a sine of pi half multiplied by 2, and this will give you number 2. If you want a sine wave of 100 Hz frequency and we want it to have bias of 2, then we just add sine of 2 pi 100t plus twice sine 2 pi 0t plus pi half. If we add a few signs together, there are places where they add up, and at other places they can cancel each other. This way we can build very sophisticated signal shapes. Okay, here is one more interesting example where sawtooth signal is approximated by an increasing number of sinusoidal waves. The black plot has only 2 sinusoids. The blue plot has one more sinusoid added, so it becomes a little bit closer to the original signal of sawtooth. And green has 5 sinusoidal waves. So as you can see, when we're getting more and more signs inside that sum, we get closer and closer approximations. And here is red plot, which has 100 sinusoidal waves inside, so it's kind of very close to the original signal. So as you can see, a list of amplitudes of the sine waves can describe the shape of a given signal. The amplitudes of sine waves as a function of frequency are called the amplitude spectrum of the signal. This is what we typically use to analyze signal properties. In other words, we want to know how big the sinusoidal components of some signals are at a particular frequency. There is also the phase spectrum, where we plot phase as a function of frequency, but it is less used in practice. Pay attention that in natural signals, the coefficients that multiply signs are typically getting smaller and smaller with increasing frequency. Sometimes people call it power law. The usefulness of Fourier transforms is very easy to demonstrate. Many times it is difficult to see oscillatory patterns in the time domain directly because of noise and complex signal structure. Here's one example of a signal which looks like pure noise. But if you plot its amplitude spectrum, you can clearly see sinusoidal components at 5 and 10 kHz. In Fourier transforms, frequency is a continuous variable, but since computers cannot handle continuous variables, we just sweep frequencies on a discrete grid and get amplitude and phase values of sinusoidal components. Before we define DFT, we need to clarify a few assumptions of DFT and define a few important variables. First, we assume that the given signal X has capital N samples. To make DFT work, we assume that the function repeats infinitely outside of the defined endpoints that you have. So the same endpoints repeat over and over again from minus infinity in time to plus infinity in time. This is our assumption. And from practical perspective, it doesn't matter if the real signal is not really periodic, because all we care about is about those endpoints that we are investigating. The time between samples is defined as delta t. This means that the length of the signal in samples should be n times delta t. The index n is a time index, and it runs from 0 to capital N minus 1. And the index k denotes the frequency index, and it also runs from 0 to capital N minus 1. So you have exactly the same number of components in the time signal and in the frequency domain. The formula for computing DFT from a signal X includes complex functions, so I will not get into details here. But for each frequency component k, one can find the appropriate complex value of the transform DFT, which we call Fourier coefficients, and we denote them by capital C of k. The absolute value of the Fourier coefficients is the amplitude spectrum. The angle of complex Fourier coefficients is the phase spectrum. If you know Z transforms, the DFT is just Z transform of evenly sampled on a unit circle points. For example, you have a short piece of music here. And the amplitude spectrum looks like that. Clearly, most of the sound is concentrated in frequencies below 5 kHz. But look what happens to frequencies 40 kHz and higher. There are many strong amplitudes there as well. More than that, they have mirror symmetry with the low frequencies. In reality, there are no sinusoids in that range of frequencies which are above 40 kHz. But they will always appear in DFT. The thing is that only the left part of the spectrum is useful, and the right half of the spectrum always mirrors the image from the left. The frequency in the middle of the spectrum is half of the sampling frequency, and is also called Nyquist frequency. So left to the Nyquist frequency is what we need to consider. The example also shows one obvious problem. We know that particular sinusoidal components have larger or smaller amplitudes, but we do not know when that happens. The music changes in time, but DFT does not tell you how. It gives you kind of time-averaged amplitudes. To get time variation, we need to use shorter pieces of a signal. We call them windows. And then we can compute DFT for each window separately, even with windows overlapping in time. And using this process, we can build spectrograms. But this is topic for another video. Alright, now I want to show you how to compute spectrums in MATLAB. So let's define some artificial signal, which we'll call X, and you can see the plot of that X in the picture here. So to define that signal, we will decide on the sampling frequency first, and we will say this is 1000 samples per second. We call it f of s. Then the sampling period will be 1 divided by that frequency. The number of samples that we will have is 1000 samples, which means it's 1 second. And we define the input variable n as numbers from 0 to n minus 1. So each sample will have its own number, n. If you want to convert it into time in seconds, we need to multiply that by sampling period t, and we will get variable t. So let's define now the x. So x will be 1/2 multiplied by sine of 2 pi 100t, and 100 will be frequency in hertz. And the second component will be amplitude 1 times cosine of 2 pi 300t, and 300 will be frequency of the cosine wave. Now pay attention that sine and cosine are connected by shifting sine by 90 degrees. So practically both of them are sinusoidal waves. So we want to get back information if the signal is sine or cosine and what frequency it has. So we compute fast Fourier transform using FFT function of MATLAB, and then we normalize the amplitude to convert it into real amplitudes. And here we multiply it by 2 because, as you remember, in the spectrum you have two parts which are symmetrical, and the energy distributes evenly on those two parts, but we check only one part, only left side of the spectrum, so we practically ignore the right side. So we need to double the values that we get on the left. And also we want to do that by sample, so we need to divide by n variable. And that's it. So S will be our spectrum. And then we just need to plot spectrum S as a function of f, which is function of frequency. As you can see, we were able to replicate back all of the amplitudes of the original signal based on Fourier coefficient C of k. So we can see that amplitude 0.5 appears at 100 Hz, and amplitude of 300 at 300 Hz is 1. But we still do not know if it is sine or cosine, because amplitude is not letting us know what kind of function is that or what kind of phase you have. So to get the phase, we are moving to the next command and plotting angle of coefficient C. This angle will look like that. A little bit messy, right? But the thing is that it doesn't matter for us, because since amplitudes for most of the frequencies are near 0, it doesn't matter what phase your signal has. If you multiply it by 0, you still get 0. It doesn't matter what phase you have. All we care about is what happens at 100 Hz and what happened at 300 Hz. As you can see, one of them shows you phase of 90 degrees and another shows phase of 0 degrees. So one of them is sine, another is cosine. And this is all we wanted to know about the signals. Thank you very much for listening, and see you next time.